All right, now coming back for quantum numbers, but now we're actually going to connect them back to the wave functions that we've talked about and see a little bit more about what wave functions are, how to think about them, and what they show us. So really, quantum numbers are just a consequence of quantum mechanics. They are the natural outcome of trying to solve Schrodinger's equation, and they all represent unique solution of the Schrodinger equation here. Specifically, where we see them is in our wave functions. So in psi here, we say they're dependent on these quantum numbers. They're specifically dependent on the n, the l, and the ml quantum numbers. To make life a little bit easier here, we're going to break these up. We're going to have, instead of just psi here, we're going to break it up into r, which has coordinate space in r, whereas we have our angular functions, which are in theta and phi space. Okay, so that's how we're going to break up all of our wave functions as we try to understand them. And each one of these are going to be defined by a particular n, l, ml quantum number set. So, for example, if I look at psi, where I've defined my quantum numbers as 1, 0, 0, there's a very specific equation that I would have that represents this. This is my r part. Here is my a part. So I've got my radial, and I've got my orbital contributions to the wave functions here. And as we notice, this one is dependent specifically on r. We don't see any theta or phi in this case, but that's because of the quantum numbers we chose. And we'll see how these will change with different states. So for example, down here, if we go down to the 2, 0, 0, again, we see that there are no theta and phi terms back here in the orbital contribution. And up here in the radial part, it's still only dependent on factors of r. It is now a lot more complicated in the way it looks, but it's still that same dependence. Now, where do we get the theta and phi dependence? Is in when we start changing the m and l quantum numbers. So if we make that change here we notice we haven't changed the radial component because our n quantum number has stayed the same, but now the orbital component here is different. Don't worry about what these look like. We'll get to that here in a second. That's all we're caring is recognizing that we can break these up and they have different effects by just changing the quantum number. Okay? We'll see those graphically here in a second. We'll actually start with the radial functions here. So basically what we're saying here for each one of these is our value of psi is our y value, and our x value is going to be r. And that's what's on each one of these plots. So really what they're showing us here is where do we kind of see a value for these wave functions. Might be better if we thought about it in terms of psi square for a moment, which we thought about of probability of finding the electrons. So if we were to square these, we could learn something about that. Some characteristics that we see here is that the wave function can change sign, and specifically it's at these points that we call nodes. So I'll highlight one here in the 3p case. There's where we change signs. We also have one over here in the 2s. We have one here in the 3s. Actually, there's two in the 3s here. So there's some patterns that start to emerge in here. So for example, we find out the ns orbitals have n-1 nodes in our radial wave function. Np have n-2, and Nd we would find out has n-3. So if I look up here, I've got a 3D, so I've got 3 minus 3, which equals 0. And if I look in here, there's no place where I see a change of sign. So that all checks out. What I'm not showing here is the f orbitals. What do you think the equation would be there? Probably a pretty good pattern that we can see at this point. Now, if we want to use this to look into probability, what we're going to have to do is use what we call the radial distribution function, which is still looking at the square of this r of r, but now there's this 4 pi r squared. Don't necessarily worry about the mathematics of where this comes from. Really think about this. This is just thinking of what is psi squared specifically in terms of the radial component here. So now we can actually use these in terms of probability. Over here on the left-hand side, let's look. I've got the 1s orbital, and notice it peaks very close to the nucleus, very small radius. The 2s peaks farther out, and the 3s peaks out even further. But also notice there are other peaks. So for example, for the 3s, we can find one down here It's not the maximum, but definitely you can find it there. We also find it here as well. So there are places that we find it, not just in one specific location. There are multiple places. But the big thing to notice is that as we increase the n quantum number, the most likely position of that electron gets moved further and further out. If we want to compare the S, P, and D functions, we can see what happens there. So here's all of them for n equals 3. In this set, we'll see that the most probable position for the S is farther away from the nucleus than the P and the D. So the D electrons are actually closer to the nucleus than the S electrons in this case. That has some important consequences. One thing that we have to remember, just like we saw over on the left-hand side, just because these are the most likely positions, that's not the only positions. So look down here. This is another place where we can find 3s. So most of the time, we'll find that the 3s electrons are most likely here. But sometimes we find them all the way in here, closer than the P or the D. Not always, just sometimes. That will have important consequences on when we talk about shielding a little bit later on. I think the angular functions are a little bit easier for most students because you've had more experience with these without even realizing it. The angular functions are just our orbitals. So if we're looking at what we have here, these are described by our L and ML quantum numbers. If L is equal to 0, there's only one possible ML state, that is ML equals 0. I have one shape, one orientation. It's a sphere. If I look at L equals 1, then I can have ML equals plus and minus 1 and 0. I have 3 distinct choices because I have 3 distinct p orbitals. How they're different is because they are on different axes for each one of those orientations. That's what each of the ML is representing to us. If we go down to L equals 2, now we have our d orbitals here. We have 5 of them. 1, 2, 3, 4 of them kind of look like our flower models, and here's that one that's a little bit awkward. This is an important one that we'll talk about frequently throughout the semester. When we go down to the f orbitals, they kind of look like three-dimensional flowers now, so we've got more lobes to them, and that's just generally the process, is that each time we go down to a new orbital, we add on more complexity to it. We won't have to worry about the F2 frequently for this course, but it is good to know and good to have at least seen them before. They look similar, but some characteristic differences. And again, just as a quick reminder here is when we are looking at different ML quantum numbers, we could say that we have the plus 1, we have the 0, we have the minus 1. It's not necessarily how they'll work out. Don't worry about which one belongs to which one. That's all they're showing is different orientations. Big thing to notice that these orbitals are all 90 degrees separated. This is when we talked about orthogonality way back when. We said if we had 2 unique wave functions and we took their integral, they should be equal to 0. That's what happens when we have these orbitals at 90 degrees to each other. That makes those functions multiplied together equal to 0. That's an important component of why these functions are allowable in the greater scheme of things. We can also see, though, that the n quantum number does affect the look of these orbitals. So, for example, let's compare the 2pz versus the 3pz. And they look similar in that they both kind of have that dumbbell type shape. But if we look here in the 3p, we see that we have a node between these two areas, a node here, and a node here. So we see changes. So basically, we're starting to see the shell effect because we could draw, for example, let me take these away for a moment to clear that up. But I could draw a shell around here and a shell around here. So we're seeing the shell effect of that n quantum value here. It's just not as easy to see here because now we're dealing with the theta and the phi space here. All right. That's what we need to recognize here, is that they look the same, but we see radial nodes starting to appear in them. Those nodes are right here. In a second here, we'll see the same thing with the d orbitals, but since we're dealing with inorganic, we're going to be dealing with d orbitals a lot. One thing that you need to commit to memory is what d orbital has what shape. Don't worry about these labels of EG and T2G. We'll get to those later. Right now, you need to know the shape. Easiest way to remember this is the DXY, the DXZ, and the DYZ are all the same plot. We just change which axis. So here we've got XY, so I've got Y and X. Here I've got the XZ, I've got X and Z. Here I've got ZY, Y, and Z. It's the same plot, we're just swapping which axis we have. That just leaves two that are kind of unique, the DZ squared and the DX squared minus Y squared. The difference of the X squared minus Y squared, notice that now it's on the axis rather than in between the axes like we saw below here. Okay? Make sure you know those. Make sure you know how to label them. That will be very important as we move forward. Just like the p orbitals, we'll see that these d orbitals can look different as we go to higher quantum numbers. So for example, here I have the dz squared, which has this donut shape around my dumbbell. I still have that when I go down to the 4dz squared. Here's my donut. Here is my dumbbell. But notice now I have my radial node that's coming in here. If we look over in the case of the 3dx versus the 4dx, here we've got our flower shape for both of them, but now I have a radial node going along here. All right, so that's what we're going to see in terms of node structure on these and how these things connect. But remember, these are all still connecting to our quantum numbers. Here I have 3, that's my n quantum number. D is telling me about my L. The XY is telling me about our ML quantum number. That's the connection here. They're all solutions from the Schrodinger equation, which is one of our favorite things to say that everything is due to. All right? This stuff is probably complicated. We're going to have to talk about this in class, I'm sure, from time to time. So don't hesitate to ask questions for clarifications. Let me know what I need to do to help you better understand material, and we'll get you going. All right? That'll do it for this one. Till next time, be excellent to each other.